All right, so we want to take a look at a few definitions before we get too far along. So the word thermal, it's an adjective and it means of or relating to heat. All right, temperature is a noun. So we went through quite a bit of discussion about the difference between heat and temperature. All right, but essentially temperature is a relative scale. All right, that's comparing the amount of, or the relative presence of heat in an object. And then heat is a form of energy. We went all through this a couple weeks ago. So let's talk about two different types of heat. One type of heat is sensible heat. The other one is latent heat. So sensible heat means that it's molecular excitement in an object. Okay, so it causes something to expand and contract, right? Latent heat is heat that is absorbed into an element through the change of state. In that diagram right there, you can see that we have a solid, right? And to change a solid into a gas, right, or into a liquid, requires a certain amount of energy. And I think this is water that we're looking at, okay? So you start adding energy, so it gets heat energy to a point, and we talked about how it's not going to change in temperature for a long time because you're going to keep adding energy. Energy's on this scale, and temperature's over here. So it gets above the point where it turns into a liquid, and now it's liquid. Now you start adding energy, and the liquid starts to warm up. Okay. Now look how much energy it takes to turn it from a liquid to a vapor. So remember, energy is on this scale. So to go from a solid to a liquid was not too much, but it's a massive amount of energy required to go from a liquid to vapor. And that is latent heat. All right? So taking a look at units of temperature, we've already sort of looked at this before, but we'll take a look at it again. There is the Celsius and the Fahrenheit scale. Those are the two scales that we're predominantly sort of familiar with. So both of them are based on water freezing and water boiling. And so the Celsius scale makes a lot more sense when you think of it as water freezes at 0 and it melts, or it boils at 100. The Fahrenheit scale predates the Celsius scale, and it's the one that we still use in this country, and water boils at 212 and it freezes at 32 degrees. All right. Units of heat. We are, like I mentioned before, the only country on the face of the planet, or the only major country on the face of the planet that still continues to use the British thermal units. The British even gave up on it. So take a look at the third item in the definition. It is the amount of heat energy that's required to raise 1 pound, not a gallon, but 1 pound of water by 1 degree Fahrenheit. Okay? So when you look at the SI units, joules or watts, which is what most of the other developed nations in the world use, they're looking at it as 4.18 joules is required to raise 1 gram of water by 1 degree Celsius. All right? They're both kind of coming at it from the same kind of factors, but the systems are different. All right, so taking a look at temperature versus the sense of touch. All right, two items can be the same temperature but feel really, really different when we touch them. So I got up there, I love chocolate chip cupcakes, right? Or I love chocolate chip muffins. But think about it. Most of you, if that tray was in the oven, you could probably manage to pull out a muffin, right? And you could bounce it around in your hand and not get burned, but you could probably just start eating it, right? Even if it just came out of the oven. But what about that pan? Did you guys grab that pan with your bare hands?
No.
No. So you have to be careful about how much heat is in something because there are other factors like conduction and conductance that come into play, okay? So let's talk about human thermal comfort, and then there's a second PowerPoint that goes with this one that we'll go back into the other room to cover. So we're warm-blooded animals, okay? We have to maintain an internal body temperature, not a surface temperature, but our internal body temperature somewhere around 98.6 degrees, all right? Our skin temperature at 92 degrees is fairly common, all right? We produce heat energy. The only way that you're not going to produce heat energy is if you're dead. So we are producing heat energy through thermogenic processes, all right? And the heat production is always going to be positive as long as we're alive. The amount of heat that we as humans or animals produce is based upon what we're doing. We're all sitting around chilling, trying to stay awake through Iggy's lecture, right? So we're not doing a whole lot of energy. But imagine if we ran up and down those stairs 10 times. After coming up and down those stairs 10 times, you'd be pretty hot, right? Because your muscles were basically using chemical energy, right? And they were producing heat as they were doing it. Come on, you gonna make it?
Yeah.
Huh? All right. So let's take a look at metabolic levels, and we'll tie it to BTUs, right? So when you guys are sleeping, believe it or not, you are burning calories. All right, so 300 BTUs per hour when you're sleeping. Like right now, you guys are sitting around relaxing, chilling, trying to stay awake, trying to go from 300 to 400, right? Or actually, you're trying to stay at 400 and not get to 300. Because at 300, you guys will fall asleep and you won't listen to me. Right? Brian's over there and the CTI is nodding his head. All right, if you guys are walking, you're burning about 750 BTUs per hour. And if you guys are climbing stairs, you're burning 4,400 BTUs per hour. Okay? So, human body wants to maintain temperature equilibrium. All right? So we take a look at, an engine that's running normally, and as long as the engine's cooling system, right, keeps the temperature of that water that's running through the motor or the coolant at a certain temperature, we're good. But guess what? If the radiator stops working or some other part of the cooling system doesn't work, it overheats, right? Just like that car, we've got to figure out a way to maintain equilibrium. Our bodies have to. So if we go running up and down those stairs, we're going to sweat. Sweat's going to evaporate. You guys remember how much energy it took? Remember that graph that showed taking a solid water and a little bit of energy to convert it to a liquid, and then there was a massive amount of energy that was used to convert it to vapor. Well, when we sweat, we're taking liquid, right, and we're turning it into vapor on the skin of on our skin. And so that is absorbing a massive amount of heat. Can't be helped. I've got to get through this. All right, so our bodies want to stay at that temperature, and so if it's too hot, then we sweat. The sweat hopefully evaporates. If it's cold, we end up like that poor guy right there, right? He's shivering, trying to stay warm. I think there were people at Design Village that were doing that the other day.
That was you, Iggy.
Yes, it was me. All right. Okay, so the environment around us has a huge impact on how we maintain our equilibrium. Okay, remember our discussion earlier about the different types of environments, whether it was hot and humid or cold and wet. So those things are going to come into play in trying to maintain our internal temperature. Right? So if our internal temperature drops below 98.6, the body's losing too much heat. Remember, it wants to stay in equilibrium, right? And so when the body starts to lose too much heat, it needs to warm up. If it's balanced, it's good, it's comfortable. It doesn't have to do anything other than to live. But remember, we are always producing heat, so we've got to be able to be getting rid of heat at a rate that keeps our temperature at 98.6. Right? If it gets too hot, our body is retaining the heat and can't get rid of it fast enough. It's got to do something to get rid of the heat. So, what happens to the human body when the temperatures are not at optimal? Well, when you get when your internal core temperature gets to 97, you begin to notice you're cold, right? So when the core temperature drops to 95, we begin to shiver and you get goosebumps on your skin, right? If our core temperature drops to 85, that's our internal core temperature, we pretty much lose power of speech. You're in hypothermia at that point, okay? If it ever drops to 72 degrees, you've done irreparable damage to portions of your body. Design notes. No, it wasn't that bad. All right, so let's go the opposite direction now, right? At 100 degrees of internal temperature, you start to sweat really bad. So if any of you have sat in a sauna, that's what you did. You kind of raised your internal body temperature, okay? At 105 degrees, we start to basically get nauseous, and it's extreme nausea. At 107, we pretty much pass out. At 110, we have brain damage and we'll probably die. So the mechanisms that the human body uses to try to maintain equilibrium are referred to as homeothermic mechanisms, okay? So the human body is going to basically start with level 1 at vasomotor adjustment. So vasoconstriction is going to basically start to reduce the amount of blood flow near the skin, because the blood flow as it comes close to the skin is how we lose heat. So if it's cold outside, it's going to basically constrict the blood vessels and try to keep the temperature warm as much as it can. In a warm environment, when it's hot, it dilates the blood vessels and allows the heat to flow closer to the skin, which then allows us to lose our heat through sweating, evaporation, and radiation. All right? So I think we're going to stop here, and we'll pick it up in the other room for part 2. This one got really long, I know. I was looking at me going, my God, what a long lecture.